Hi, our names are Dalton Labar, Kanan Chijima, and Emma Wood, and our formal lab report one was about inelastic collisions. The goal of our investigation was to determine the relationship between height at which an object is dropped and the amount of energy transferred out of its system as internal energy. Therefore, our research question was, how does the height at which a golf ball is dropped impact the amount of energy transferred out of the system as internal energy? The prior knowledge that we used is listed in these bullet points below. The first prior knowledge is that in inelastic collisions, the total kinetic energy of the system is not conserved. Therefore, the coefficient of restitution calculates the fraction of kinetic energy lost. Furthermore, kinetic energy equals the gravitational potential energy. In a 1D collision, momentum is conserved before and after collision. P initial must equal P final. Our experimental design was that we dropped a golf ball from 4 different heights, 0.2, 0.4, 0.6, and 0.8 meters, to observe the velocities of the ball between trials and then analyze the transfer of energy. Our independent variable was height, dependent variables were position, velocity, and the change in energy, and our constant variables was the mass and shape of golf ball controlled by using the same ball, initial velocity, which was 0 meters per second released from the height, but this cannot be perfectly controlled. Tracker was used to create a position versus time graph with a line of best fit from the 4 points immediately before and after the ball's collision with the ground. This line of best fit represents the velocity of the collision.
When constructing this experiment, we listed some possible sources of error, one of which being velocity, as initial velocity is not always going to be zero, timing, as there are some delays in human reaction time, and height measurement, as a meter stick has a certain amount of error due to the distance between each mark. To reduce this error, we had the video recorded from a constant distance. We used a meter stick that was flush against a wall and had its base on the ground to reduce parallax error. Here are some visual representations. On the left is the system schema, and then on the right you can see the motion diagrams and the energy diagram, which shows that from a greater height, there is a greater amount of total energy. And then you can also see that the closer the ball gets to the floor, the greater the amount of kinetic energy and also the greater amount of internal energy.
The 0.2 meter fall, we show the screenshots of the ball falling before collision and after collision. We observe the velocity before hitting the ground to be negative 1.87 meters per second, and we use this observed velocity to calculate the kinetic energy. This gave us the kinetic energy before hitting the ground to be 0.0803 joules. The tracker also gave us a standard error, which was plus or minus 0.07 meters per second. We use the same equation used in which was the kinetic energy equation and use the observed velocity after hitting the ground as well. Then we calculated the percent energy lost as internal energy.
For the 0.4 meter fall, we found that the velocity before hitting the ground was negative 2.6 meters per second with a standard error of plus or minus 0.1. And then we calculated kinetic energy to be 0.1551 joules. And then after hitting the ground, the velocity was 2.31 meters per second with a standard error of plus or minus 0.05 and a kinetic energy of 0.1225. So then we calculated the percent energy lost as internal energy to be 21.02 plus or minus 4%.
For our 0.6 meter fall, we had an observed velocity calculated on tracker using those 4-point tangents. That observed velocity was negative 2.8 meters per second. We found a kinetic energy of 0.1779 joules, and our standard error calculated by tracker was plus or minus 0.2. After hitting the ground, we had an observed velocity of 2.6 meters per second, a kinetic energy of 0.15514 joules, and a standard error of plus or minus 0.2. Our percent energy lost as internal energy was 13.76 plus or minus 10%. For our 0.8 meter fall, before hitting the ground, we had a velocity of negative 3 meters per second, a kinetic energy of 0.20655 joules, and a standard error of plus or minus 0.07. After hitting the ground, we had a higher observed velocity, which is impossible, of 3.4 meters per second, a kinetic energy of 0.26530 joules, and a standard error of plus or minus 0.02. We found energy was gained in this trial. We found that 28.44% plus or minus 2.4% was gained during this collision. For our results and conclusion, we found that as height increases, potential energy increases. As height increases, the time taken for the ball to hit the ground increases, and therefore the velocity at which the ball hits the ground increases as well. When the ball hits the ground, the ball only bounces to a fraction of its original height and its velocity decreases. And the biggest takeaway is that as height increases, potential energy and subsequent kinetic energy increases, and therefore the loss of energy as internal energy increases, and the collision becomes more inelastic